Good morning, all of you. Actually, I'm waiting for the expert to join. Actually, he's having some network issue, so we'll be starting sooner. Please keep patience. Okay. Good morning, sir.
Yeah, good morning, good morning. Good
So,
morning. Yeah.
Good morning, sir. So,
Good
so
morning.
let me start the session, sir.
Yes.
So all the participants, welcome back to the third day of Fundamental of Quantum Computing course. So today we are having our beloved sir, Professor Amlan Chakraborty. He is just a minute.
Oh,
Let
Shumanta
me
is also
introduce.
there. Shumanta, good
Good
morning.
morning, sir. Good morning.
Shumanta is also my student.
Yes, sir. Yes, sir.
So good to see.
So
Okay.
today we are speaking on
Correct,
quantum.
yeah.
Yeah.
Yes,
Shumanta, you were not there in VLSI design. Why?
Huh, sir.
VLSI design happened in Kolkata and you are not
Yes,
there.
I know everything. Yeah. Actually, I have
Okay,
other
please go
tasks.
on. Please.
Uh,
Yeah. So let me introduce Professor Amlan Chakraborty. Actually, he is a known figure. But still, from my side, I need to introduce him. Professor Amlan Chakraborty is a full professor of information technology in A.K. Chaudhary School of Information Technology at University of Calcutta. His research areas of mainly quantum computing, embedded system, VLSI design, computer vision, and whatnot. Actually, so actually, if I start saying about him, so it will not stop today. So it's better to keep it shorter. So thank you. So his topic of discussion is fundamentals of quantum machine learning. So I request her to start the session.
Thank you. Yeah. Thank you, Professor Shamapado. Thank you, Professor Shumanto. Right. Both are very close to me. right? And thanks for inviting me in this particular faculty development program. Yes, I will speak on quantum machine learning. And as you know that quantum machine learning is that means after you know quantum computing, you can get into this quantum machine learning. But so what I have planned that I will have a preliminary of this. So what's the duration of this lecture, Shamapada? What's the duration?
Sir, actually, I have kept 2 hours. Now,
2 hours. Okay, fine,
it is
fine. That will be fine for me. That will be fine for me. I will be very comfortable. So what I will do, I will introduce the basic concepts of quantum computing required to understand this quantum machine learning, and then I will go to quantum machine learning. I will go slowly, and I will try to give a pause in between, maybe after each 15-20 minutes, so that faculty's kind of questions I can get back to them. Okay. So let me start my presentation. Let me start my presentation. Okay. So screen. Okay. Yeah. Okay. So tell me that if it is visible.
Yes, sir, it is visible, sir.
If it's visible, right?
Yes, sir.
Okay. So let me make it full screen. So it's visible perfectly, right?
Yes, yes, sir. Yes, sir.
Okay.
Fine.
Okay. So the title of my talk is Unlocking the Quantum Frontier, which means that actually now we are in a particular, that means you know that that means we are very lucky that just I think a day ago, the National Quantum Mission funding funding proposal call, right, has been confirmed. And I hope by January end, the call will come up. So we are at a very important juncture, right, at present, where quantum computing is now becoming a new frontier paradigm for computing. Okay. And so the target is that how we can use the quantum computing into different types of solving different types of computing problems. Okay, now having said so, it is obvious that it is still an exploration phase. It is not that we have got enough amount of computing problems where we have shown that okay, quantum computer can do wonders. But obviously there are a good number of problems where it has been already proved that quantum computing can do wonders. And we know that the current levels of computing problems, right, also considers machine learning as an important domain. So now the next step of quantum computing will be, or it's already started, is that whether we can use or leverage quantum computing for machine learning. And what I will discuss today is basically what are the things which are embedded or deeply seated in the quantum computing domain, and which can be leveraged and which can be very efficiently used, okay, to do the machine learning applications. And that will be the second phase of my lecture. So first phase of my lecture, I will discuss about basically the quantum states, right? How the quantum states work and what are the operations we can perform the quantum states, so that from the quantum states we can get into the feature space, quantum feature space, and then we can get into the quantum kernels, and then we can get into that how we can define a machine learning problem in the quantum paradigm. Okay, so this is my agenda. Obviously, the basics of quantum machine learning and the circuits and some of the use cases, and obviously we will come to the quantum research, University of Calcutta, and challenges and considerations at the end of my talk. Okay, so this is this particular picture speaks about that how we have emerged in the computing paradigms. The different computing paradigms were existing, starting from the early computing paradigms, which were the electromechanical, and then the valve computing. Okay, then the circuits based on the valves came. And then in the middle, or the most striking or the most significant part of computing is done on silicon, and still is done on silicon, right? It started from the discovery of the transistors in Bell Labs that means I think in the late 1940s, right? And then the silicon silicon transistors, okay, take a lead role, right, in designing our digital hardware, okay, computing systems like processors and controllers, as well as memories, right? And the miniaturization of this particular transistors led to the enormous effect or enormous technological progress towards the presently the SoCs, system on chip. So we have miniaturized systems which are built entirely on a single chip, right? And these chips are pretty strong, and they're very powerful, right? Compared to the maybe the computers 10 or 20 years ago, right? And they're driving our mobile systems, they're driving our cars, they're driving our every electronic components, very complex, complex data processing they can do, right, with a small amount of silicon, okay? Now, as we are moving towards the squeezing of the size of the transistor, obviously, I think many of you know that the present size of the transistor is around 3 nanometers, okay, or 2 nanometers, right? I think Intel has come up with a 1.5 nanometer process, okay, so which is really something technologically remarkable stuff, okay. But when we are going to this particular regime of matter, right? Obviously, we are in the domain of the transistors or our computing circuits, which are itself of one atomic layer thickness. Okay. Now the question is that whether can we use the atoms as our computing atomic states or subatomic states as our computing right, as our computing states. Now, and that leads to the quantum computing because the laws by which these atomic states or subatomic states are being controlled, are being maneuvered, they are the quantum laws of physics. Okay, and you can argue that, sir, quantum laws of physics were always there, right? But what we didn't speak quantum, because atoms were there, right? Subatomic particles are there, like neutrons were there, protons were there, electrons were there. Okay, so now they were all defined by the quantum physical phenomenon. Now, why we didn't speak about quantum computing at that point of time? Because at that point of time, our observation capability, our control capability was not at that level where we can observe this atomic and subatomic particle and control this atomic or subatomic particle and fabricate this atomic particles and on as desired, right? That technology was not there, right? So instead, what we did bulk semiconductors or bulk matters, where we have several strands of these atoms, right, which makes the bulk. And when we go into that particular state, right, our electrodynamics, doesn't resembles same as the discrete quantum dynamics what we have in the individual atomic states. So now we have the power and the capability to observe, to control, to maneuver this type of states of matter, which are inherently quantum states. We can interact with those states, and so we can do computing with those states. Okay. So now, if you tell me that what is computing in a very nutshell, that in a very abstracted way, what is computing, right? So if we look into computing means that you are actually doing a controlled update of your data, right? And that data resides in the memory. So your memory state gets updated in a as per a particular logic of computation, and you start at some value of your memory state, which we call initialization, right? And then you do certain operations on the memory state. It may be a single memory state, it may be multiple memory states, whatever is that, defined by the as you know, in terms of programming, we tell variables, right? And we update those variables in the process of computation. And ultimately, we stop at a point when we have reached or we have finished all the desired operations to be done on the different memory states, and then we just do the readout of the memory states, and we take that as an output. Okay, I hope that this is what is simple computation. Okay, now, so now any computer system which can perform these operations on the memory state. Okay, so first of all, we require a computing system. If you are defining a new paradigm of computing, suppose, okay, so what the paradigm should offer us? The paradigm should offer us a way to store the information, right, in the memory state. There should be some sort of definition that how we can store the information, and there should be some sort of process by which we can update these memory states. So if we tell that, hey, these are the atomic states, so we have to have some means by which we can represent information using atomic states. Okay, and there should be some means by which we can do the do operations or do the some sort of transformations of these memory states to certain operations which can be performed in this particular paradigm of computing, and we can evolve with the updated memory state of the system, right? And this can be done in a very controlled fashion. So if we can do that, then we are coming up with a new computing paradigm. And obviously the second question comes that why we at all do it? Why we at all move to this computing paradigm? Do we have any sort of efficiency gain? Yes. So the thing is that obviously when we look into a new computing paradigm, like we can tell the GPU system is a new computing paradigm, right? Right. I met the CTO of NVIDIA a couple of months ago in Delhi. Mr. Jansen, he was really a very, very dynamic and one of the very top CEOs I have met, right, in my entire professional career, right? He met individually few of the researchers all over the country, and I was lucky to be a part of that team, right? So NVIDIA said that we started a new computing paradigm, right, using the GPU-based parallelization of many cores. Okay. Similarly, quantum computer can also, we can say, a new computing paradigm which exploits the atomic state of data representation, and which also works on the transformation of this data, right, based on some sort of operations of the atomic states. Okay. So now I show this physical quantum computer. Okay. And now we can, this is a little bit old figure of quantum computer, but this is a very understandable quantum computer architecture. And when I started my research at Indian Statistical Institute, right, around 2005, right, that means we didn't have this image at all, right? But I started the research quantum computing, right? And the physical image of quantum computer was just like just nothing to me, right? We only understood that, okay, the principles of operations, but the physical system was not there. Physical system came around 2011 when I was at Princeton. Okay, so okay, but now that means who are researching in quantum computing or who are trying to develop courses in quantum computing, they have a pretty good advantage because the physical quantum computing systems are there, right? And this is one of the images of such systems, right? You see a lot of wires, bunches of wires, right? And then there is a quantum chip which sits here, right? All these wires are because we require a lot of these control signals. And also there are a lot of cryogenics. So this particular chamber is a dilution refrigerator chamber, which gets this, which makes the system cool, right? Because we know that quantum states are very fragile. So to maintain the quantum state, right, with a very low error or low noise, you need to maintain a temperature which is sub-zero Kelvin. Okay, so this is the cryogenics, and this is, but but nowadays people are trying to make it more what I can more compact, right? I have seen some of the things which are coming up now, right? They are more compact and they are more less number of VARs and less number of this particular channels are there because they are making the things very very sophisticated. Okay. Now coming back to quantum computing is that what we are exactly doing in quantum computers, or what we are exactly doing by developing a computing model over these atomic states, is that we are leveraging certain things which are not there in classical. Okay, so what we are leveraging, the things called entanglement, superposition, and interference, which actually follows the duality of particle and wave. Okay, so particle and wave has a duality. Okay, so either we observe as particle or we observe as wave, and this particular and the matter at this particular state has this duality, that they can also exist as particle and also exist as at wave functions. Okay, and this peculiar property of the matter in this particular gives us some sort of principles which were not there in classical. Okay, and these principles are superposition, entanglement, and interference, and we will discuss a few of them in this particular lecture and how they influences computing. Okay, now let's go into the very fundamentals of this. Okay, so when we look into the memory representation of data, right, that's the most important thing when we start computing, that how data will be represented and stored in the memory. So we know that in the classical computing, the data storage is in terms of bits, okay, which I show in the left hand side. And bits have two possible states. Okay, it's a logic high, which is a state 1, and logic low, which is a state 0. So you can have a particular bit, right, either storing a value 0 or storing a value 1. Now if you come to quantum bits, which is shown in the right side, right, so the quantum bits, okay, can be represented by, instead of a press button switch, it is presented as a slider. So the slider can be at anywhere, right? It can be at one end, which represents the 0 value, and at the extreme other end, which represents the 1 value. But the slider can be in between also, right? So it means that it is somewhere in between 0 and 1. Or we can tell that means if it is exactly in between, then we can say that it has a 50% of projection on 1 and 50% projection on 0. Or we can slide it a little bit towards 0, which means it is a more projection on 0 and less projection on 1. Or we can put it a little bit towards 1. We can tell that it's more projection on 1 and less projection on 0. So these are the things which we can do it, okay, which we can do, right? So this is the peculiarity, or this is the uniqueness of a quantum bit, which means, and these states which are between 0 and 1 are called superposition states, okay? And this is for a single qubit. Now we exploit the superposition states in a multi-qubit quantum system, and we can show that in a multi-qubit quantum system, using superposition, we can span the entire vector space. Okay, I will come to this. If I had a board, I will try to show you that we can span the entire data space. So this is what's the advantage of these quantum computers, that using a small amount of data, right, you can span a large amount of the space. You can large amount of such space. Okay, you can represent a larger amount of data using smaller resource. Okay, I will come to that very soon. Okay. Okay, the other side of it is that, as I say, that is what are the different options of superposition. So this is again an analogy which I show the classical on the left, which is only two possible values. In the quantum, right, the states of a single qubit quantum system, the states of a single qubit quantum system is represented by a sphere, which is called a Bloch sphere. Okay. Now, what are the important things we have to know about the Bloch sphere? Okay, this sphere has a radius 1. Okay, it's also called a unit sphere. Okay, this sphere has a radius 1, which means that a vector which I start from the center of the sphere, right, and I can align either to 0 or which is up vector up, or I can align to 1, which is down vector, right? Its amplitude can be maximally 1. Okay, now what happens. Okay, let me just use a sort of pointer. Okay, pen. Okay, now what happens when a vector is here, okay, which is being shown by this particular state, okay, on the surface. You have to remember these are all surface states. Okay, so all the surface states, because ultimate magnitude of all these vectors will be 1. Okay, so all the possible quantum states, as I represent I represent this superposition like a slider switch, right? But it is actually, in terms of the quantum state vectors, it is actually represented by a sphere, and so if the vector is purely up, it represents 0. I think this is red, and red is sorry. If the vector is purely up, right, it represents 0. Okay, and if the vector is purely down, right, it represents 1, right, like these two states we had. Okay, the extreme 0 and extreme, but if a vector represents any point on the surface, right, it has a projection to 1 and a projection to 0. Okay, so it's a cosine value. So you take the cosine value of this, right? You take the cosine value of this, and you take the projection here. Okay, and so these are all superposed states because they can be decomposed into two basis vectors, 0 and 1. Okay, so up to this, any questions? Anyone? If any one of you have any questions, please let me know. That means it is obvious I cannot take an entire quantum machine learning, the quantum fundamental lecture due to the time, right? And as it is an FDP, I have to give one lecture. I cannot go like, but this is what I tried to make you understand the quantum state vector, and this will be pretty useful knowledge when we go into learning that how we represent the quantum feature space. Okay, so until this, if anyone has any question, please let me know. I can take maybe 1 or 2 questions if you have, or otherwise I can skip. I can just go to the next discussion. If you have any question, please let me know.
Good morning, sir. Myself, Mamta Prajapati. I'm a research scholar from Visakhapatnam, Geetham University, sir.
Okay.
Sir,
Yeah,
I
good.
just wanted.
Good that you're attending. Yeah, please tell me. Yeah.
Thank you,
question,
sir. Is this block sphere a pictorial representation of the quantum states like the qubits?
Yes. So block sphere is a representation of a single qubit state. Okay, so all the vectors will start from the center and will reach to the surface. And this all can be represented. I have only shown you the Z basis, 0 and 1. I will come across the other basis also. So what I have shown in the picture is only the Z basis. So a vector can be, if you are doing a Z basis, the vector represented by a coefficient across the 0 and a coefficient across the 1, which actually the square of there is the measurement probability of getting 0 and getting 1 out of the vector when we measure. Okay,
sir. Yes, sir.
Yeah.
So its importance is the visuality of the states, pictorial representation of the states.
Very important, and that I will help you to make understand that how the feature vectors can be generated, because otherwise you cannot come to the conceptualization of the feature values, how you encode the feature values into the quantum states, right, and use this for computation. So this vector, this quantum state vector, knowledge of quantum state vector is very important. Yes.
Yes, sir. That's what it's regarding its importance, and a more elaborate regarding this block sphere. I just wanted to know, sir.
I will come to
Yes,
this.
sir.
It will be it will be more expanded when I will come to the use of basis, right?
Yes,
and
sir.
I hope you will get some more understanding on that in the next part of my lecture. Yes.
Yes, sir. Thank you so much, sir.
Okay. So I think there is no more questions. So I will let me go back to my presentation once again. Okay. So I hope it is visible the screen.
Yes, sir. Yes, sir.
Okay, good. Okay. So we know that yeah, machine learning, right? That means it's now what I can say. It's now a term which is the equivalent to quantum computing. Okay. I may be speaking a joke, but this is now coming in a great way that it is quantum computing means machine learning, right? Which is not actually, which is not. There are enough computing algorithms which you can do exactly, which you can have a very beautiful functional description of it, functional form of it, right? You do machine learning only when you don't find the proper way to describe the the functions which can be explored in the domain. Then you try to generate an hypothesis out of the data and the results generated in the domain and try to form a sort of model. But now if you look into the students' demand and students' projects and whatever happening is everything is now, it seems like machine learning is everywhere. Okay. So now understanding the machine learning is something that we try to look into the patterns in the data, right? Patterns in the data means that you can actually you can actually try to find out that what are the kernel operations, right, which can be maximized in this particular data, because the kernels are your patterns. Okay. So provided you can, okay, you can find the appropriate kernels, right, and extract the patterns, right, you can predict, or you can classify, or you can tell that what is your data about. Okay. So this is what is in the summary, what is the machine learning. Okay. Now, quantum computing is obviously, I've described quantum computing, right? Quantum computing is basically how we can exploit the quantum mechanical phenomenon, right, of matters, right, in atomic and subatomic levels of matters, and we can exploit it in computing, right? How we can describe the memory states, like we have discussed a little bit in my previous slides, and then how we can transform those states, memory states, and we can tell that we are doing computation. And then how we can read out those memory states, and we can tell that, hey, we have got the result what is required. Okay, so this is what is quantum computing, and this is doing in the quantum mechanical way is quantum computing. Okay, now quantum machine learning is a sort of domain of quantum computing, or a sort of strategy we try to develop in the quantum computing paradigm, which can speed up the machine learning algorithms. Okay, whether we can show a sort of we can show a sort of betterment, goodness, right, in implementing the machine learning algorithm in the quantum domain. Okay, and that's the focus, right? It's not a very thumb rule that, hey, that okay, whatever machine learning is that quantum computing will do good. No, it's not like that, right? So the way that's the deep thought we have to do. We have to do a sort of analysis of these algorithms and try to find that how they can map in the quantum domain well, right? Without any biasness, right? Though I am a quantum computing prolific researcher in quantum computing, but I don't have a quantum computing bias. But I will not say that, okay, that means everything in quantum computing you can do. It's not. No, it's not like that. Okay. So you have to understand it's just like a parallel, it's just like an accelerator sort of stuff, right? You know, a lot of accelerators are coming up in hardware and software in HPC, right? Where obviously you cannot accelerate the entire program, right? Or you cannot accelerate all the programs. There are some scope of accelerations, and then you exploit the accelerator, and then you accelerate your program. Same in the case of quantum computing, right? These are called quantum computing accelerators. So if you find a suitable way where quantum computing can be exploited, right, put it into the quantum machine and get it accelerated, get that computation accelerated, right? right? And then again, come back to the classical and do your work. So it will be a classical computer exchange. I will come to this latter part of my lecture, okay? So machine learning, when I say it doesn't mean that, okay, that means everything is in quantum, okay? So it will be some part of the machine learning, or maybe some steps of the machine learning, right, will come in the quantum acceleration phase, okay? And that we are trying to see that how we can do it, okay, in this particular lecture. I will try to explain that to all of you. Okay, so so machine learning in a very summarized way, we can say machine learning can be two types. One is supervised, where you use the data and build the models, right? Use the data means use label data, okay? Sorry, use label data. So we know that, hey, this particular data, right, domain expert has labeled it, and it has been said that this particular data is that the outcome is this or that, and that we try to take as a training data, right, and try to build a hypothesis, right, which actually maps the data to the outcome, right? And if you are pretty close enough for the large amount of training data that all the training data maps to the desired outcome, training data as the input, which is the feature space actually. The training data is nothing but we give generate a feature space out of the training data, right? And the inference on the feature space leads to a conclusion, right? And this conclusion maps the original conclusion in the most of the cases, or all of the cases, when we say that the model is built. And then obviously it can work with the new data, and it can generate the inference, right, of the domain based on the domain, because it has already learned the domain, okay? Sorry. So the best example of this is that I give a face of a person, right? That means either it detects it's a face, also it can do recognition that whose face is these. Okay. Now in the case of unsupervised learning, right, there are different ways of unsupervised learning. The principle of unsupervised learning is that you only get the data, right? You don't get the expertise level, okay? So what you can do, you can only try to give a response to the data, right? So one type of response is very simply, which are clustering techniques, where we try to tell that, hey, if you give me a large bundle of data, right, getting into the feature space, I can tell that, okay, this group of data are very closely associated, and this group of data are not associated with the other group, but they are associated with this particular group of data. So there are different types of groups of data we can identify, right? And also what we can do, we can also do a process called generative learning, which means that without giving any clue to what is the outcome, right, I can still take certain inputs, and I can generate, okay, some outcome, right? And this outcome with a sort of discriminator, okay, can tell whether I have reached my goal properly or not. And that is what is a generative learning model. So generative learning model is a process by which you generate some random outcomes, and then you try to see that whether the outcome is as per the requirement, which is called a sort of, we can pick a discriminator, and it can tell that, hey, the outcome is good or bad. It will not actually give any other information about the data, okay? So this type of generative modeling, which is very much predominant in the present case, depends a lot on the random generation of the data, right? And a quantum computer can actually do a very good random generation of data, because quantum computers are inherently random. Okay, so that is one of the directions where quantum computing is hitting towards. That here, that means that a generative model, which means that, hey, you have a large amount of data, right? Generate the randomly generate a large amount of data, and then you try to apply some sort of rules, right? Some sort of filters, right? And try to squeeze out the needed data. Okay, so now in this particular case, might be quantum computing can do good because it can generate a large amount of random distribution. Okay, and if you look into the if you look into the domain of neural network, which is also very important, I show the neural network left and right, okay? So what I have in left is the classical neural network. So classical neural network is something which consists of nodes. And in each of the nodes, certain amount of computation works. Okay, what it does, the basic computation, what it does is that it does a multiplication of the weights and the data coming from the previous nodes. So each of these links from node to node consists of a weight. And when I say that, hey, I have a value V here, right? And how it comes here is something like, hey, if I have a value W, it's W is the weight. So I multiply W with V and put it here. Now it is not only one node contributing to this particular node, right? This is the network. So it means that there are n number of nodes which are connected to this node. And what we do, we actually do all those weights multiplied by input from the previous node and accumulate it to the node. And then if we wish, we can actually use a sort of function, okay, right? And that function can actually give it can be a thresholding function, which can tell that, hey, the accumulated value is pretty high or the accumulated value is pretty low. So it does a sort of, okay, thresholding of this particular data, right? And these functions, okay, and these functions are functions like you have the functions like sigmoid, you have the functions like ReLU. These are called activation functions, which means that depending on the previous input nodes, and depending on the weights by which these input values are being scaled and passed to the next node, this node can fire or might not fire. This node can be activated or might not be activated, right? And the activation of the previous activation information, this you can do at each node, or you can keep the data only. Okay, so whatever you have done, again it goes to the next node, and again there are weights which gets connected, right? And this way it goes on, and ultimately we come to a particular level or a particular layer where the taking the decision is very easy, right? I can tell that after all this feature, and this each of the layers are called generates a feature map. And after starting from the primary feature space to the next level feature space, analyzing all the feature space and trying to understand that wherever input has generated high and wherever input generated low, I can actually take a gross assumption of the features, and I can actually tell about this particular, this input. Either I can classify this input, or I can tell that what is the predicted value, right? Which I can generate from this input. So this is what is essentially a neural network, okay? A classical neural network. But when you go to the quantum neural network, these node operations, okay, will be nothing but, you say that you weight multiplied by input and then gets accumulated, right, with the inputs from the other nodes. Now, these operations are equivalent to the change of the vector state. So the vector state was in one orientation, and then due to all these operations, the vector state's orientation gets changed. Okay, I will come to why these orientations are important, because these orientations actually generates the value what we measure out of the vector during the measurement. Okay, and so the changing orientations is one of the very important thing. That is, so these orientations are done by the rotation gates. In this quantum network, you see that these are the lines, okay? And these lines signify that these are nothing but qubits. And these blocks are nothing but the single, if it works on one line, it means that these operations are done on a single qubit. So these operations are modulating the qubit states of a single block sphere, because these are working on single qubit lines. So a single block sphere state is modified, updated by these operations. And what they will do, they will actually change the position or the orientation of the vector in respect to one of the axes. I will come to the axis very soon. Apart from that, there are operations which combines 2 qubits like this. Okay. Now logically, you can have 3 qubit, 4 qubit operations also, which is not shown here. But when we come to a specific technology, okay, it is well understood by all of us. The technology only supports, all the technology which are at present supports only 1 qubit and 2 qubit operations. Okay, they will not support higher than 2 qubit operations. Though logically we can have multiple qubit operations. So there is some technique called quantum circuit synthesis. So quantum circuit synthesis is a technique by which you can actually take a large quantum circuit and you can synthesize it in terms of basic quantum logic operations, which are something like this, 1 qubit and 2 qubit. So ultimately, which gets implemented in a quantum machine, at this point of time, the technology is still, you have to, this is 1 qubit and 2 qubit gates. Now, what are these 2 qubit gates are different than 1 qubit gates? 2 qubit gates works on 2 qubit states. And these two qubits generates a coupling between the 2 qubit states. And they generates a particular distribution. I will come to this very soon. These 2 qubits generate a particular distribution which you cannot get by only operating 1 qubit gates. So here I can stop. Here I can stop and I can come back to the, as there are faculties, I will give a very interesting question to the faculties. Okay. So how the distribution and the machine learning problem. Okay. Suppose I take the example of classification. How a classification problem in machine learning is related to the distribution of a system, right, at its output. Who can tell this? Who can answer this question? How the distribution of the outcome of the states and the decision or the inference of a machine learning engine can be correlated. Do you have any answer on that? Anyone can try. I will have a little bit of biscuits in that time. Yeah, please go on. If any faculty has any answer, otherwise I will give the answer. So again, I repeat my question that how the distribution of the outcome and your classification outcome can be correlated. Or rather, I will make a question simpler. Can the outcome of a classification engine is a distribution? Yes or no?
Yes.
Excellent. Good answer. So can you explain it? Why?
Sir, it represents actually the states, state vectors, which would actually obviously will come into.
Don't consider quantum now. You just tell that a normal classical, whatever is my classifier, a classifier generates a distribution outcome. Okay, that is outcome. So how we can tell that, okay, this is a good classification algorithm, or this actually we are looking into classification only.
Normally it should fit in any of the distributions, sir. Only then we can say that the classification algorithm works.
Very good.
Fine.
Very good. So
yeah,
so we accept that. So we accept that.
So
yeah.
And
yeah, very good. So we accept that if you are trying to achieve a classification,
by nature it should follow a distribution.
Yeah. So we accept that if you are trying to develop,
as in the data are related, so we work on the relationship rather than.
Yeah.
Yes.
So suppose we have. Yeah. Hello. Can you listen to me? Can you hear me? Can you hear me? Hello?
Yes, sir. Yes, sir.
Okay. Okay. So
yes,
so if we were trying to generate a classifier, right, for each of my input, okay, which I'm trying to classify, I will get a distribution of the outcome. And this distribution can actually tell that which class this particular is that, because each of my input, right? Or we can extrapolate it a little bit more. If I have a superposed input space where all the data has been captured in a superposed state, and then if I generate a polar distribution of the classes then I can find, at least I can tell that, okay, among the input distribution where there was no class, I can come out with a distribution where I can identify that, okay, these are the distribution of classes in my data. So all these things can be done if we have a distribution in the outcome, and the distribution of the outcome can be correlated with the classification outcome. So we are now all of us now agree that this works. So quantum computing gives you a very good scope of generating distributions in a very controlled manner. And these generative distributions can be well mapped through the training process, through the class levels, right? For the specific training, during the training period, we associate the distributions with specific class level for a specific set of data in the feature space, right? And then we can actually do the classification as a distribution, and we can generate those distribution using this 1 qubit and 2 qubit. A 2 qubit gate operations can generate certain distributions which 1 qubit gate alone cannot do. And that I will now come now, right? So this, I think, is very clear that how distributions helps, okay? And machine learning works in distribution very well. Okay, so now I will come to the discussion once again. I think one of the participants, said that if it can be better discussed, okay? So I again come to this because this is very important now, okay? So I hope my screen is visible to all of you, right? Because I'm switching it between discussions and screen, okay? So it's visible to all of you, my screen?
Yes, sir.
Okay, great. So again, I come back to the blood sphere. I add some more things here in the blood sphere, okay? And that's very important, okay? So this axis, which is this is called a z-axis of the or the z basis of the blood sphere, okay? This is called the y basis, and this is called the x basis of the blood sphere, okay? So we have a good variability. Why? Because a quantum state is represented by this particular notation, psi. This is a ket notation. It defines that psi is within a ket, within a line, and there is an angular brace, okay? So this is a typical ket notation which we just take from the quantum physics. So quantum physics tells that any quantum state is being defined in terms of ket notation. So once I tell that psi is a ket, then okay, in this way it means that psi is a quantum state. So now this quantum state is represented by this vector. Okay, I think all of this here. And this is a two-dimensional representation of the blood sphere, where we assume that this vector is on the surface. All good? Now, there are three axes. So I said that if psi represents a data, then I have to compute on the data. Means I have to update the data. So what's the update on psi? If it has to be a quantum state, because when you update it, it should be again a quantum state. So psi should be psi dash, where psi dash is on the quantum state. So if I want to do psi to psi dash, the vector should map to any other point on the sphere except this point. Right? Is it clear to all of you? So what are the psi dashes? There are infinite number of psi dashes can be possible. So if I telling that I have to change the state of the quantum state, I have to update the quantum state, means from psi it will move to psi dash. And what is a psi dash? Psi dash is again a quantum state. And what is a single qubit quantum state? And what is a single quantum? This will be again a point on the surface. So this vector will now have to reorient itself to another position, right? And it can be either an operation around X, or a rotation around Y, or a rotation around Z, or a much complicated, which is a combination of X, Y, and Z. Am I clear to all of you?
Yes, sir.
Am I clear to all of you?
Yes, sir.
Yes, sir.
So this is this is my job is done. I have made you understand that what is quantum computing. Single qubit quantum computing. Yes or no? The single qubit quantum computing means, hey, you generate a quantum state psi, which represents a point in the Bloch sphere. And this will have its own orientation across X, Y, and Z axis. And then you just twist and turn this particular vector to any other point in the Bloch sphere, right? And it gets the change of the state psi dash. And to do that, you do all possible operations across X, Y, and Z. One step, two step, three step, four step, whatever it is. Ultimately, you will reach to any of the side dashes here, all over the sphere. And that's quantum computing, right? And then you measure it, and then you come back, and then you tell, hey, the way here the measurement was a measurement. Okay, then again a good question. Sorry, there's another question. So where do you measure? Measurement across Z-axis, measurement across X-axis, measurement across Y-axis is very different. The same vector will have different values. Okay, and this leads to another hint. All these axes are orthogonal, and this correlates to the feature space. Is it true? This all orthogonal axis generates a feature space. So this is so important. Okay, so the entire feature space game can be so well conceived in quantum computing because you have so many basis states to play with. So this is what we do the quantum game. And those who understands that this quantum game, they are very sure that what operations needs to be done. Though it is not always supported by technology. And this work we did lot earlier, for instance, when we developed the FTQLS tool in Princeton, and I was the lead researcher of the particular tool, fault-tolerant quantum logic synthesis. Though you can tell the professor, can I take this to this? Can this state can be converted to this, and just tell me that what will be the operations required? There is a limitation that when we try to do it in a real physical technology, the rotation operations, what we need to do across the axes, Rx, Ry, and Rz, these are multiples of pi by 4. We cannot do rotations which are some multiples of pi by 5 or pi by 6 or pi by 7, something, or pi by 8, something like that. So theoretically they are possible, but technically they are not possible. So there are certain errors and limitations of the quantum state updates. Okay, so this is also something we have to take care. Okay, so some examples, it has been said here that Pauli X is a pi rotation across X. Hadamard is a pi by 2 rotation across Y, and then pi rotation across X, which creates an equal superposition of 0 or 1. So this is this line. Okay, this line. Okay, so this line is something an equal superposition of 0 and 1. So this are certain. These are only a few operations. Okay, it's not. It's only 2 operations I mentioned. There are a lot of operations are there in the quantum computing. One thing more, I think, which is not there here is that, okay, yes, the last line is there, okay. The last line, a unitary 2x2 matrix. Actually, any quantum operation is a unitary operation. Can anyone tell me what the unitary operation means? Or what are the properties of unitary operation? Anyone? Yeah, this may be a student level question, sorry. Yeah.
Reversible, non-singular.
Yeah.
And yeah.
So determinant should be 1, right? It should be a square matrix, right? It should have an identity. Identity is obvious. right? Unitary matrix have a guaranteed identity, yes or no?
Yes.
Yes, right. And this identity is also very simple to derive. The simple derivation of a unitary matrix identity is that that means assuming that, and actually quantum matrices are that all the coefficients are complex. All the coefficients are complex. So you take a conjugate transpose of a matrix U. Conjugate transpose means you do the conjugate of all the coefficients and then take a transpose, and that is called U dagger. And U dagger is actually the U inverse. So getting the inverse is guaranteed. If you have a unitary matrix U, you have a guaranteed U dagger, which is its U inverse. And U inverse is I. And this also leads to some concept called reversibility in quantum computing. So what it means that suppose a state psi is here, right? So you apply a U and you take it to psi dash here. And then on psi dash, you apply U dagger. Where it will fall. Okay.
Back to psi again.
Yeah, back to psi again, because U dagger is I. So it's actually U dagger psi means I psi. So maybe U psi is psi dash. But when I again apply U dagger to psi dash, it means that U dagger U psi, which is I psi, which means psi remains, psi goes back here. So these are beautiful techniques, okay, of computation, unrolling your computation or uncomputing your computation, which doesn't have any classical equivalence. So if you are knowledgeable enough in quantum computing, you can use these resources and you can try to find out that how I can benefit in specific algorithms, okay, to apply these techniques and get this done. Okay, am I clear to all? Now let's move, okay? So this is the game of basis, okay? So this is one basis, this is one basis, this is, and they're commonly known as 0, 1 basis, Z basis, minus plus basis, X basis, and plus I minus A. Mostly we use the Z and X basis, okay? Y basis is hardly used, okay, for measurement, okay? Now I come to entanglement, okay? So I show you a multi-qubit quantum state string, okay? So let me know that whether you get this particular string representation. Who all are not getting this, please ask me. Please ask me that. That means I will help you. Okay, so just look into this particular, I will just use a pointer. Because I feel I'm taking a class, right? Those are faculties, but I'm still taking a class. Okay, so please go through this string, all the participants, okay? And try to understand that what this is a quantum state, multi-qubit quantum state. Can we appreciate this multi-qubit quantum state? This is a superposition multi-qubit quantum states. Okay, having 2 to the power n basis states. For a single qubit, how many bases we have? What is a basis state in vector space? Yeah, single qubit, 2 states. In a vector space, a basis state is that any state can be represented as a combination of the basis state. So rightly answered that it's a single qubit. There are 2 basis states, 0 and 1. Okay, so any qubit can be represented as a superposition of 0 and 1. Now, if we go on increasing from 1 to 2 qubit, there will be 4 basis states. 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. If you have n qubit, it will have 2 to the power n basis states. So what does it mean? It means that you can have 2 to the power n data elements represented by n qubit state. This is the power of quantum computer. And you can do it at one shot. Okay, so means that if you are using a quantum, if you are using a classical memory, suppose this is a 3-bit classical memory, you can only store one of the 3-bit values out of 000 to 111. You can only store any one of the 3-bit values. Whereas in a classical computer, if you are using a 3-bit classical computer, 3-qubit quantum computer, you can store a superposition of all the values from 000 to 111. And such a superposition has been showed where the number of qubits is n. The coefficient summed will be obviously the modulus square will be 1 because the probability of all the states will be summed to 1. And the amplitude square is the probability. And the summation of amplitude square of all the states will be 1. Okay. Now we show two superpositions. This is a 2-qubit superposition. So it will have states 000, 011, 011. And this superposition can be easily decomposed into 2 independent qubit states. So this is the conversion we can always do. So two single qubit input qubits can generate a multi-qubit states by their tensor product of each of the qubit states. And this comes here. And these 2 qubit states can be again decomposed into 2 particular qubit states. And these type of states are called bipartite states and not entangled states. But now come to this particular 2 qubit state. This is also 2 qubit state because if you have 00 and 11. So 00 and 11 comes only when there are 2 qubits. But this 2 qubit state cannot be decomposed into 2 independent qubit states because you don't have any A and any B or any C and any D, which this qubit 1 and qubit 2 tensor generates this value. And this is the unique thing in the quantum computer, which is called the entanglement. And the entanglement are non-bipartite states. Means you cannot decompose this particular states into 2 independent qubit states. Okay. And these are pretty important. And there's also another thing you have to observe here, right? So what you can observe, right? Suppose you measure the first qubit. Okay. So first qubit you measure and there's an equal probability of 0, 0 and 1, 1. So first qubit you measure, it can be 0 if it is entirely collapsed to the system has collapsed to 0, 0 state, or it may be 1 if the system has entirely collapsed to 1, 1 state. But the thing is that if you get the first bit as 0, you are pretty sure the second bit is also 0. You don't have to measure the second bit. Similarly, if you get the first bit as 1, you automatically get the second bit as also 1. You don't have to measure the second bit. So, and there are several these type of combinations of 2 qubit and multi-qubit entanglement. And this helps us both in computing and communication. In communication, when you are doing a passing of message between multiple parties, if you can generate entangled qubits, automatically the information which is being generated at qubit 1 at the location 1 is automatically taken over by the entangled qubit at location 2. But it's not so easy to generate multi-party entanglement in a distant communication. There are specialized techniques to do that. Okay, I'm not getting into this because this is more a quantum computing discussion, not a quantum communication. Okay, but quantum communication uses this, and they are called Bell states. So Bell states are used, and there are teleportation techniques which use Bell states, by which you can pass a quantum state information without using a quantum channel. You can use these entangled Bell states, and you can use this in combination with the quantum information what you have in location 1. And if you pass the measurement information from location 1, measurement means you can now generate classical. You can now push into classical channel, because once you measure, data becomes classical. So you can use a Bell state and you can use a quantum state at the location A, and you can do a measurement using the Bell state. And that measurement value you propagate to the location B. And in location B, if you have the same Bell state passed in some quantum channel, then you can regenerate the data at location A. So these are how the quantum communication called teleportation works. Okay. And these are, again, maybe in other discussion, I will do that, right? I do a lot of work with this in communication. That means with industry like HCL and other, we did a lot of, and also with CDAT, we work in this type of applications of the quantum states. Okay, let's move on. So this is what is the analogy.
Hello?
We have the
Yes.
AND or NOT gates, XOR gates in the
Hello.
Hello. Yes.
Yes, sir. So I have a question. In the
Please,
previous
please.
slide, for n qubit system, there were
Yes.
two raised to power n basis vectors.
Yes.
So why this is the linear combination is up to 2 to power n minus 1?
No, this is I, the index I. The index, if you take the index I, it not
Yes,
starts from C1, it starts from C0. So
Okay,
it is actually 2 to the power n numbers, but the indices.
The indexed, okay.
Yes.
Okay.
Indices are 0 to 2 to the power n minus 1. Okay, fine. Okay. So these are the classical qubits, classical logic operations, and these are the fundamental quantum operations. Okay, you can argue, sir, when you go to literature, we find so many multi-qubit operations, MCT operations in different forms, but you have to understand these are the primitive quantum operations. Okay, so whatever quantum operations we do in high level, ultimately they have decomposed into single qubit operations, which are nothing but one qubit operations across X, Y, and Z, or two qubit operations involving multiple qubits. Okay, combining their values across X basis or Y basis or Z basis. Okay, Z axis. Okay. So now let's go a little bit deeper how the rotation gates work. So you see that this was the state of the qubit. You can just assign a vector also here. Rotation gate changes it to here, right? And this obviously have a different measurements. So if we measure this across Z basis, you will get a high 0, 1, 0, and 0, 1. But when you rotate it and do it, right, if we measure now on Z basis, you will get a some value on 0 and some value on 1. So this is how the quantum superposition works, right? Which may be a little bit difficult to understand in terms of that if you don't understand the state vector. Okay. So it is not something which we are doing very different. It's only the interpretation leads us to the combination of 0 and 1. Okay. And these rotations we can do across all the axes, across X, across Y, across Z, and these are called RX, RY, and RZ operations. Okay. And this is how it works. Okay. So they can generate distribution. I'm not getting into this. So you can just make a certain initialization of your qubit and do a rotation, and that rotation can generate equal distribution of zeros and of 0 and 1. Similarly, if you have some bias, if you start the qubit in this particular thing, and if you rotate it with some value, then you have a different distribution. So the distribution of the class levels for a particular quantum state representing a particular data in your classical represents how you just orient the vector. So if you are training across the levels and you're trying to maximize that data for one particular level and minimize for all for the other level or other levels, right? You have to just in the training, you have to just associate the rotation vectors in a proper way so that after measurement, it falls with a high probability in that level. Okay, am I clear to all of you? Okay, the big question is that that means I think you should ask me that, sir, how difficult it is to understand these rotation values. So this is the whether it is superpasses or surpasses the complexity of the classical. Yeah, the complexity of assigning the rotation values are really critical, and you require some optimizer for that. But remember, these are done in the training time. In the runtime, this system will be pretty fast because they can generate the distribution at a one shot, at O1 time. You can generate the entire data space at O1 time, right? And you can generate several state vectors with multiple qubits. And then you can actually make these state vectors measured in the buckets, right? As per the training data. And then your problem of a big data problem in quantum computing possibly can be done in a better way. Now, having said all this, we have to really establish this. Okay, there are a lot of skeptic in quantum. There are people skeptic in quantum. I am not a skeptic and not a bias also. I am in mid. So I try to see if something better can be done in quantum. Let's go ahead. If not, let's remain in classical. Okay, so we have to explore this, and we have started this. So maybe 2 months down the line, if you tell me that, sir, that means, see, that what I'm discussing today in this lecture is only the quantum machine learning, how to approach quantum machine learning, right? I haven't said you anything about a particular algorithm, quantum machine learning. This I didn't say because we are just finishing a quantum, though we have done quantum soft computing algorithm. I will come to that, the ant colony application. But quantum machine learning, we're just finishing a very close work we are doing with a group, right? And I hope the results will come soon. And maybe 2 months down the line, I will tell that, hey, this is and when I do solution, I do solution for generalized solutions. I am pretty skeptic in telling that, hey, this particular solution having this particular instance of the problem worked well. This doesn't work very good for me in algorithmic point of view. If you are telling that, okay, this works well, you have to work a generalized problem, right? And quantum machine learning in a generalized problem is a challenge, okay, because there are a lot of things you have to take into consideration. But we are almost close to one of the solutions, and we will disclose that maybe 2 months down the line, okay, if it works well for us. So I'm not discussing anything of the problems we have solved, but we are all discussing the materials you can use for quantum machine learning. Okay, that's the lecture, my lecture. Okay. So now if you are looking into distribution of your states, and that can be a part of your machine learning approach, general distributions, which many of the pioneers in that means I was with many of the stalwarts in computing in one of the ISI presentations very recently I gave. Okay, and many of the stalwarts appreciated that, yes, that this particular viewpoint of mine, that quantum computing can generate distributions and it can help machine learning, is really a strong point to take away, okay, to take forward, okay. And these researchers should work more and more, okay, instead of just trying to crunch the application by using the equivalent quantum operations. You have to look into the bigger dimension of the problem in terms of distribution. So let's see how distribution works. Okay, so there are 2 qubits now. Okay, we show that there are 2 qubits. Okay, and these 2 qubits with different types of biasness and different types of rotation. This is a very good distribution where we have 25% of all the possible states, 0, 0, 0, 1, 1, 0, 1, 1. So using a 2 qubit, you can represent 4 possible buckets. Okay, using n qubit, you can represent 2 to the power n possible buckets. And this is a very good distribution. All the buckets are equally filled. Okay, But can we produce a distribution where two of the states have high values, 50-50%, the rest are all zero? Now this cannot be done using simple rotation gates. To do this gates, we require the entanglement. We require 2-qubit gates, okay? And these are the possible distributions when we involve 2-qubit gates. These are not entangled at all. These are maximally entangled. These are in between. So you can see that different types of distributions can be generated by the combination of single qubit rotation and entangled gates. And this distribution helps us in machine learning. Okay, this is the takeaway. I will just skip a bit. So now this distribution requires the knowledge of the theta of the single qubit operations and multi-qubit operations, and what to apply in which qubit line. So these are all terms of your training the quantum circuit. So this is a quantum circuit now. Okay, so this is a very big view of quantum circuit. So you have the quantum states initialized, and you have the measurement at the last of the quantum states, and intermediate you have several quantum operations. Okay, and there are two main parameters of quantum circuit. One is called the number of qubits, qubit depth, and one is the circuit depth. So the size of the quantum problem depends on number of qubits and number of size. At the present, the quantum system doesn't have large number of qubits. We are at the NISQ. So if you are trying to exploit large qubit systems, these will be very noisy. So if you are trying to make less noisy system, you have to work with small qubits. So this is limited. And the circuit depth also, you cannot work with long circuit depth. You have to work with smaller circuit depth, because longer circuit depth means with time, you are operating on the qubit states more operations, and that will decoher the quantum states. So both the circuit depth and the qubit depth are limited in terms of the present quantum scenario, which is NISQ. NISQ started with less than 100. Now IBM has touched 1000 qubits. Still it is NISQ. It will go beyond NISQ and the proper quantum computer when we have the 5000 qubits. And the good point is that the achievement of 5000 qubits has been declared by some of the strong, powerful the organization's quantum computer, which will be coming in 2025, 2026. So we expect that 2025, 2026, we will have a boom where a lot of algorithms will be now mapped with a serious effort to the quantum computers, and the supremacy will be well tested and will be well driven. Okay, so the quantum algorithms for which I started my PhD, like Shor, Grover, right? HHL came a little bit later when I was at Princeton. HHL came. Okay, so these algorithms were the unitary matrix were well defined. There were no parameterized unitary matrix. Okay, means there is no training component in unitary. When you have parameterized, means you need to set the parameters. So there you need the training. Okay, but once we come the optimization algorithms and this quantum machine learning, PQC is not post-quantum cryptography, mind it, is parameterized quantum circuit. So PQC is also post-quantum cryptography, which is another domain, which means that suppose this cryptography analysis can be done very well by the quantum systems very fast, then how to prevent quantum systems by attacking your systems? Then you use some sort of cryptography which is called post-quantum cryptography. But here, PQC, which is mean parameterized quantum circuits, which is the theta part of the U. You have seen the RX, RY, RZ theta, and you also seen XX, YY, and ZZ theta components. So those theta components are the components which you need to adjust, which you need to learn. These are similarly the weights of a neural network. Okay. So there are different ways we do it, right? We have to organize the circuits. I'm not getting into details of this. These are some of the circuit organizations you need to do. We need to, there are several levels. That means you can come up with a circuit which is like this, but you cannot implement the circuit because in the present technology, all the qubits are nearly associated. So you cannot have the long circuits like, hey, a Q2 is now controlling Q7. No, you cannot do it because you have to do it in the nearby nearby qubits. Actually, my PhD work was one of the key contribution in my PhD work was to model this nearest neighbor components or nearest neighbor association functionally, how it influences the algorithms and the quantum circuits, right? In my PhD, this is a major contribution of my work was this, right? And it's still playing very good because we are still at the nearest neighbor. We were still at the NISQ set of computing. So when we start with this type of circuit in a high level, but when we try to make it towards the technology, we come a circuit like this, where all the operations are very close to one another, because you have only few qubits which are nearby. Okay. Next part, I come the encoding scheme, right? How you map your data from the classical domain to the quantum domain. So whenever you try to map a data to the classical to the quantum domain, you have to define a sort of quantum vector we can represent your data and see how a quantum vector can represent your data. So a phi can oscillate between 0 to pi. Okay. So you can have 8 movements from 0 to pi, and you can have 8 different qubit states, rotation across z-axis. Okay, you can increase further. You can increase further the feature space because these are all independent. Okay, so the feature you encode in X is across this, and then you encode the feature across Y, which is across this, right? And then you encode feature across. So this is feature across X, and you can also encode the feature. So this feature across Y. Yeah, this is the rotation across Y. Yeah. So you can do all these type of rotations, and you can increase the feature because these all are orthogonal. X, Y, Z are orthogonal, and you can generate the feature space, feature values which are orthogonal to each other in the feature space by generating rotations across the different axes in the quantum states, quantum state vectors. Okay. And then comes that is how we settle out the theta. So this theta is again something we do in class. So as I said, the classical quantum will go hand in hand. Right? It is not that a quantum will just work isolated. So the parameter tuning of the gates will be used as a loss function optimization, and it will be a sort of feedback, and we update the parameters similarly as we update the weights, and try to slowly get to the parameters which gives a very low loss value. Okay. And in order to do this, we have a lot of decompositions of the R theta gates. They are decomposed vertically, horizontally, a mix of horizontal and vertical. All these things we can do. Okay. And so at the end, I come to the context of quantum learning. So what is quantum learning then? So quantum learning means that you have to encode. So in the classical, what we do in classical, we actually take a data X, we map it to the feature space, and then we apply a kernel which can try to find out the peaks and troughs in the feature space. Where my peaks are, where my troughs are. Peaks may be class 1, troughs may be class 0. So that's all we do. So we do a sort of estimation, okay, based on the feature space, and the estimation is done on the kernel function. Kernel function will give a high and a low value, and that will define what is my data. Okay, what is the prediction of my data. So in the quantum, what do you do? We take an X and we create an equivalent quantum state representation phi X. We use a quantum kernel to actually move the phi X and take it to the high or low in the measurement space, similarly as the classical kernel does. Right? And then we measure, and then we find that some measurements giving high and some measurements giving low. Or we can have a distribution across the classes. right? And we can tell that which particular data falls in which class. Okay. So I'm just skipping a bit. So these are the quantum circuit. This is the statistical way that you try to encode that stuff. You generate a kernel, measure it, generate the feature map, and you get it done. Okay. So in a nutshell, that a lot of things are there in between. So obviously the IBM platform, the IBM Qiskit, right? I hope that some of the experts have already discussed this. I think might be Amit. He said me that he has a lecture here, maybe a lecture yesterday. Dr. Amit, my PhD student, right? So we know that, okay, this so this is a good platform which many of the quantum computer giants are now doing. This is an IBM platform. Similarly, we have an NVIDIA platform. Okay, so what they are doing, that see that for a normal software developer, is very difficult to understand the nitty-gritties of quantum computing. He or she will just use the quantum libraries, and it will just pass the parameters to the quantum libraries by which the programmers work, right? Developers work. Okay, research works. Research is a support to those. First, we generate research, make the libraries, make the system stable, and then we pass it to the developers so that they can use it. So this is a tool chain that IBM has done. So what do? You take the user applications, generate the quantum equivalent. Obviously, there are a lot of research work is here. How we generate the quantum equivalent of a given user specification. Look, we are also working on a project which is a quantum software development lifecycle. Okay, that means the important aspect how we generate the quantumness, or how we generate a quantum requisition from the user description, and then it is mapped to the quantum operations. Okay, first the high-level logical operations for runtime primitives, and then we pass to the physical quantum chips, which are called QPUs. And when we pass the high-level quantum instructions to the QPUs, you have to map with the controllers, which sequence the instructions, which actually makes the actual physical thing workable. Okay, and this is and you know that when we tell 1,000 qubits quantum computer, it means that it is not on one QPU, multiple QPUs. So it is a better, or it is already the assumption is that already the things working out is that it's multiple QPUs we work with. Okay. There are a lot of applications, right? We are working with a lot of startups, and I will very happy to that means if any one of you also start with developing applications. So the applications are basically on finance, applications are basically on drug design, applications are basically on material search, right? Applications are basically on security, also on portfolio management, resource optimization. So a lot of business applications, because now we are also looking that, okay, we understand the quantum, okay, that how we can map a business problem to a quantum perspective. And the most important part is that can we show the speed up, okay, with the limited resource of quantum what we have, and can we predict that, okay, once the quantum system is full-fledged, we will have enough supremacy. Okay, though Google and other companies have already stated that there's a good amount of supremacy. Okay, there are a lot of applications and quantum articles are there. I'm not getting into details due to the time, right? That means I will be free to discuss in other opportunity, or you can just do one-to-one discussion with me. A lot of things we have discussed with the principal scientific advisor. A lot of quantum NMQTA discussions have happened, both at MIT level, both at DST level. We are fine to, okay, we will do, but there are certain challenges. Okay, noisy quantum hardware. I said that qubit depth and circuit depth both are limited. We cannot go into the high scale due to the noise. As I said, qubit availability is one of the thing, gate depth is one of the thing. Complexity of quantum programming. It's not so easy to come up with a new quantum programming, right? I think you will get a very good appreciation if you come up with, sorry, quantum programming is complex because it takes the new learning for all of us. Okay, you have to learn the tools, you have to learn the libraries, you have to learn the functions what is used in quantum programming, and that is very important. Okay, classical quantum integration is very required, so it's hybrid model integration. Algorithmic stability. It is very fancy to say that, hey, I have run this quantum algorithm, but we have to tell whether it is generalized form, whether it works for a large dimension of the problem, and it does the same efficiency for the small as well as the large dimension of the problem. So the stability and the mapping of the quantum algorithm to the exact quantum system and getting out the supremacy is obviously an important thing to do. Okay. We're not get into this. This is something, right? If anybody interested in quantum, University of Calcutta, we have done good amount of work in algorithm circuits, error corrections, and new directions. I am not describing this because this is not that particular time is not there, platform. Okay, we can do it anyway. So the main things I will do, we have done enough work in quantum algorithms, and we're still doing random walk, graph search, ant colony. We are the first group in India. That means and we're the first group in the world who have developed the full quantum ant. And for developing this full quantum ant, we have received the IBM recognition in 2021, which was the first of its kind recognition in the entire country by any research group. Okay, from India, we got this recognition. Okay. We have done a lot of these automated frameworks we are doing in the pattern searching, graph searching. We have a lot of publications we have done, right, in different conferences, different journals, right. This was one of the very good work what we did with Princeton. When I came back after that, my student Mrityunjay started this work. Okay, so these are the things we did. A lot of works are there. I'm just skipping this. These are this IBM access given to University of Calcutta, the first of its kind. And then we go into the QCAD. QCAD is my PhD domain, right? Error correction has been added up with this particular domain of QCAD. We're also doing ML, okay, for quantum error correction, right? And the last year we had a paper. I think last year we have a paper at ACM-JETC, and this year we are also having a review in QIP on this particular thing, and this work is also good. A lot of things we did in Princeton, my Princeton and PhD, my postdoc, and one major was QCAD, and a lot of work we did in TVLSI, TCAD, right, in ACM-JETC, right, all the things. And this is the paper which I is mentioning in 2022, which is called IQER, which is quantum error reduction. This is done by one of my students who will be graduating soon, and who's a senior position in L&T Infotech in quantum group. Okay, Shoikat Basu. So new directions we are going getting a distributed quantum computing. QR zone is the first distributed quantum computer simulator developed by my group, which where an intern Tur Basu played a very good role, and he is now doing a PhD University of Georgia Tech, Virginia Tech. Okay, and again we with the Nanyang University. Nanyang Technology University, we are again first group with Nanyang, NTU, Anupam, okay, Professor Anupam, a very good friend. Our group developed the first binary and multi-valued quantum simulator systems. Okay, and QDLC is coming up with one of my PhD students. These are all the work we have done. The QR zone published in Spring and Nature, and we have done a lot of things in this QDIT in a lot of applications, ITP transactions and quantum QIP. And this was done in last year. Right, but this is the first simulator which involves both 2-qubit systems and multi-qubit systems together. They can simulate. It's called a QDIT platform and published in IIT Quantum Communication and SDLC. We have good work with SCL Tech, and these are the people who are doing the actual work. Okay, and okay, they are a postdoc. Most of them are graduated. Right, we have also postdoc positions, and people join postdoc, and we have good collaboration with industries like IBM, HCL, TCS, CDAC, Amazon. We also have a project with Amazon, right? And we're looking forward to more activities. Okay, right? And thank you for giving. These are good references. I will pass this PPT. These are good references where we can get the QML. All the papers are very, very first of its kind paper, and these are the predominant work in this particular domain. Okay. And these are all our papers which are published in the last few years. Okay, thank you all. And if you have any questions, yeah. If you have any questions. I hope I am within the time, Shamapada.
Yes, sir. Yes, sir. Yes, sir.
Okay. So if there are any questions, there were a couple of questions, good questions from the participants. If there are any more, I can also take a couple of them.
Hello, sir.
Yes. Yes. Please go on.
Could you please elaborate what
Hello.
measurement actually, I mean, could you make us understand what measurement is actually?
Oh, that's a very good question. So measurement is basically a probability density function. Okay. So what we try to do, we take a basis state and we try to see that if we collapse the vector on this particular basis state, right, what is the amplitude it generates? And the square of the amplitude is the probability. And that probability means if we do random measurement of the quantum state in that particular state, okay, that suppose the probability is suppose 40, which means that the state is oriented towards the x basis in such a way, and suppose it is 0 or 1. 0 is 40 and 1 is 60. Okay, so the vector is such that if you take 100 times measurement, okay, the value what we get 0 is 60 times, and value what we get 1 is 40 times. So it is actually very simple. You just take the vector, right, and you try to make it fall on the axis, right, and try to take that as its amplitude. Try the projection of it on the axis, and try to take it as the amplitude, and the square of the amplitude is the probability. So ultimately, if you are very sure that what is your initial state and what are the operations you have done Rx, Ry, Rz on the particular qubit, and what are the coupling you have done, entanglement you have done, you can easily get out that what are the distribution you expect when you measure across a particular basis. But these are all error-free. What you will get actually is that in a physical quantum system, you will get a different distribution. Then you can question that, sir, I got this distribution that means as theory, and this is the distribution because this distribution happens because the vector what you say this due to the fragileness of the quantum system has already shifted, right? And the operations what you have done exact theta, due to the fragileness, it has done theta plus theta dash. It's called the phase error. So there are the errors which occurs and which shifts the vector from the ideal, and then the distribution changes. Okay.
So one more
Good afternoon,
question.
sir.
You said
Yes, please.
in practical there are only multiple of pi by 4 rotations are possible.
Yes.
So when we take that Bloch's pair, there are
Mhm.
not there are finitely many points where it is possible to take your states. Is it right?
True.
Okay.
Perfect.
I mean, there is no
Perfect.
infinite possibility of the
Theoretically
vectors.
infinite, but technologically, still the gates are basically rotation gates a multiple of pi by 4. So that limits your how many possible quantum states. That means quantum states you can generate. True.
Okay. Okay.
Yes.
So in measurement, is it true that if you take the measurement, it will lie either to 0 or 1 or?
Yes. Obviously, you'll either 0 or 1 on the z basis or plus or minus on the x basis. But it is a probability. So it is not one measurement will not do you, not get you to any conclusion. You have to do at least certain measurements, and those are called shots. If you see the quantum machine descriptions in the reality, you will say there will shots. So shots are that you actually measure it repeatedly, right? And after a certain amount of shots, you are sure that what is the actual value you are getting.
Okay, sir.
Yeah.
So in practical, what is the measurement? In
practical, you have to do the experiment repeatedly.
Okay.
Once you measure the state collapse, you have to again reinitialize the system and measure it.
Okay, sir. Thank you. That's all.
Sir, this
Good
is
afternoon, sir.
Manju. I have a question.
Please go ahead.
Yeah, sir, when we probe into the intermediate states of this QNN, we eventually can land into any of the parameter which we did not mention in our inputs. That's what we are working on, right? So how does that can be done in QNN? Because when we measure, obviously the value is lost. So is there a way to probe in the intermediate state so that we could infer the data?
Yeah, so this is something backtracking you are saying, right? It's a backtracking what is done in the case of the
No,
class.
sir. It is not about backtracking. I mean, like the parameter which we never mentioned. Say, suppose you give some input, we get the output. So generally, the hidden states will infer, which will actually represent some of the parameter which is not at all mentioned in our data input data. Like if you give a weather data, we don't mention, say, suppose humidity is not given as the input parameter, and it's not even mentioned. But when we finally come out with some other output parameter is also not mentioned. But the intermediate states will give the surface of the humidity level in the data. So likewise,
I got it.
we
You are
work on such, like,
you are speaking about. I got it. You are speaking about the feature space. What we give the derived feature space from the primary
yes,
feature space,
derived
right?
feature space
Yeah.
where it doesn't hint us anything about it. Doesn't have any hint on the input or the out parameter. So
I got it.
when
I
we
got it.
want to do this in this QNN, due to
Right.
measurement the data is lost. So how do we circumvent it? That's the
So
thing.
my question is, how do we do in the, okay, so you can tell that, sir, in the classical neural network, or in CNN, that means, or you can, if you take the convolution neural network like CNN, you can tell that, okay, there are some layers we use to generate to understand the feature space, and then we can put some other type of classifiers in the front of it, so that we can get get as per the application, right? So now in the quantum neural network, getting into an intermediate state, right, will be,
Yes.
yeah, will be a sort of thing you have to measure, right? Without
Thing
measurement
is
you
that
cannot get
how
anything.
do we how can we design such probes is my question. After we design the probe, even so, after measurement the values are lost. So
Yeah,
this is hitting
so
my mind.
what do you have to do? You have to do some sort of, okay, sort of computation, right? Where if you measure early, right, and
Okay,
you
sir.
get a sample distribution, right, and you have to correlate that how this sample distribution in the intermediate measurement and the sample distribution in the outcome measurement, right, actually, how you can extrapolate the sample distribution in the intermediate measurement, and how you can extrapolate the sample distribution from the intermediate measurement sample distribution to the output, okay, to the actual output of the distribution. If you can extrapolate this, you can get certain clues. You can get certain clues that what has happened in the intermediate state, right? How was the feature space in the intermediate state, right? So that it converges to that particular in the output state, right? And that is only the clue you can get. That is only the thing you can do, right? That otherwise you cannot do anything. So whatever you have to do is have to do the interpretation between the measurements at different intervals of your quantum circuits.
Oh, okay, sir.
Yeah.
Thank you.
Yeah.
Afternoon, sir. Hello.
Yeah. Hello.
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 Yes. Good afternoon, sir. Yes, sir.
Yeah.
Are you getting me, sir?
Yes. Yeah, you're clear. Yeah.
Yes,
Please.
sir. Sir, very good afternoon, sir. Really, it was very much interesting. Sir, I'm a faculty in physics. I'm working here in Odisha in NIST. Actually, from your presentation, I got many things. The basic quantum mechanics, superpositions, unitary operator, block space. That actually we are teaching to our students. I have ample knowledge on quantum mechanics and other things, but I don't have any knowledge on the algorithm and other things. But first time I got to know that whatever we are teaching our students, it has the real applications, that it is
Yes.
astrology me. And I
Yes.
want to be part of this national quantum mission. How could I contribute and what work I can initiate? I'm very much passionate about these things.
Yeah, so the thing is that means the DST will be announcing this. I have just got a news from the DST office that they have already, the meeting has been done, which was a long-awaited meeting. And I think this will be a joint activity between Ministry of IT and Department of Science and Technology. So I think there are that means ultimately there will be some hubs will be determined. I think might be SIDAC will one of the hubs. Okay. So we have to, SIDAC Pune is trying to build on an indigenous quantum computing system, and SIDAC Bangalore is trying to develop the quantum softwares. Right. Our group will be helping both of these particular CDAC teams. Apart from that, you can look into the ISAR, right? ISAR also the people, ISAR Pune. ISAR Pune was the,
Yes,
that
sir.
means is the earlier DST quantum hub, right? They are the hub of the quantum mission. So now what you have to do there, okay, that means you have to Rapol, there's a Professor Rapol, who leads the quantum there. Right. Right. One thing is that you can club with any of the group, right? You can tell what is the contribution you can do. And then I think there will be a big team will be formed for this NMQ2A in different ways, right? And you will be obviously the part of any one of the teams. Okay. So please keep in touch. Please
Another
keep
one
in
question,
touch.
small question.
Yeah.
Yes, sir. Sir, actually, by training, I am a material scientist. Condensed matter physics was my research area, and I am working in this renewable energy, developing new innovative materials. But by side, it is fascinating me. So I think now the
No,
silicon will be used for
Government of
new
India,
materials. Yes, sir.
actually the quantum mission as one of the main pillars of quantum mission
Yes, sir.
is basically is using quantum algorithms to find new materials. So the quantum mission, one of the target is this particular thing, what you are very specialized. How to
Yes, sir.
generate good algorithms which can find that how effectively the molecules bonding can work, because you can have a lot of options, a lot
Simulation.
of possible variations in the association of molecules. So which association of molecules is the gives you the optimum result, and that is the search. Okay. So this is one of the good applications where Government of India is looking forward. Yes, you can explore this surely.
Yes, sir. The last question is whether it is the same silicon will be used, or now different materials they are searching for this quantum operations.
Silicon quantum is only being done till now by Intel. Intel is trying to focus on silicon quantum, but the IBM systems are superconducting. A lot of focus has been done in optical.
Okay. Optical.
Ion trap is
China
also coming up. Ion trap is also coming up, which can be silicon again. Yeah.
Okay. Thank you very much, sir. Thank you very much. Okay.
So thank you, sir. Thank you for your nice talk. Mainly, you have enlightened the people a lot, starting from the basic of quantum computing, from the qubit to the different areas where people can explore. You have shown the many paths, actually, many directions, so that the participants are very much benefited, I feel. And at the same time, being the organizer, I'm also very much benefited, because I am also starting this particular area for exploring the research.
This. Very good, very good.
And I need a lot of help from you.
Yeah, let's form a team and let's try to meet DST and try to place.
Yes, sir. Yes, sir. Yes,
Form
sir.
a
Yes,
team
sir,
from
right.
this only. Okay, who are interested, try to form a good team and let's try to make it to DST.
Right, sir.
Yes.
So thank you again. So,
thank you.
Okay, sir. Thank you, sir.
Thank you.
So
thank
the
you.
for the
Thank you.
participants.
Take care. I'm taking a leave. But all of you have this great FDP going on. I think are very well organized, right? And thanks for organizing FDP in quantum computing. Thank you. Thank you. Take care. Bye.
Okay.
Bye. Take care. Bye.
Okay, bye. So for the participants, I think it was a nice event, actually. You can say that we got a deep knowledge of quantum computing and its applications. So we are waiting for the third. This is the third day, and the sixth session will be on quantum cryptography. That will be given by Dr. Mrityunjay Ghosh. He is from HCL Technology. So for now, we will be ending up. So by 2:30, we'll be meeting again for our next talk. Malini Paramanande. Prima Ratne. Hello.
Yeah, hi, Shamapada. Am I audible?
Yes, Shyamapada.
Am I audible?
Yes, sir, you are audible.
Okay, perfect. So, should we start? Okay, we'll start after two to 3 minutes. No issue. Any other member should join? Will join or not?
Yes, sir, yes, sir. Just hold on for 5 minutes.
Okay.
So, how are you, sir? You are well?
Not well actually, because it is over there. Here it is a cold wave. It's basically going on for last 3-4 days in Delhi NCR. That is northern and western India. So
Okay.
yes,
I see.
actually working from home from for last 2 weeks,
Okay, okay.
and the thing is, for the last 1.5 weeks, I'm actually in fever. I have already tested COVID, but it is negative. But for the cold wave, it is going on the cold, cough, and a little bit of fever.
Okay.
Yeah, that's it.
So, sir, just let's wait for 2 to 5 minutes.
Okay. We will start 2:35. No issue.
Okay, sir.
Am I clearly audible, right?
Sir, can you take your mic a bit closer to your mouth?
Okay. Now it is audible clearly.
It's better. Yes.
Okay. Let me remove my mic actually, because I have sound system. It is audible clearly.
It's audible, yes.
Better than the previous, or mic was
Yes,
better?
yes, I think it is better.
Okay, perfect. No issue. No issue. So, okay, let's wait for 5 minutes and then we'll start. No issue.
Okay, sir.
Okay. Perfect. Should we start, Shama brother?
Yes, sir. Yes, sir. We can proceed.
Okay. Okay. Can I share my screen?
Yes, yes, sir. Please.
Yes.
So before that, sir, let me introduce you because
Yeah.
this is my job. So good afternoon, participants. So this is the sixth session. Today we are having the guest today for giving a lecture on fundamentals of quantum cryptography mainly is Dr. Mrityunjay Ghosh. Mrityunjay Ghosh is working on quantum computing for almost a decade with specialization in quantum aided cryptographic algorithms, devising novel quantum algorithms on combinatorial optimization problems, quantum walk algorithms, and quantum machine learning. He is leading the quantum activities of HCL Technologies and also active quantum research group member of IBM Quantum Network. So welcome, sir, for your kind presence. I hope that this will be an excitement session for this fundamental of quantum computing. Thank you, sir.
Yeah. Hi. Hello, everyone. My name is Mrityunjay Ghosh. I'm working on quantum computing in a research domain for 11 years, last 11 years, and also working in different development of different kind of industries like gambling industry, like optimization, then logistics, then cryptography, cybersecurity and cryptography for last 7 years. I have worked in 3 different companies, multinational companies all over the world for leading the quantum division uh, for developing new and novel quantum algorithm and developing a product around them. Right now, I'm working in HCL technology as a quantum computing principal. There we have developed some IPs, some assets, you can say resource or assets over there, on which we are actually trying to build 2 different kind of products, one based on cryptography, another based on quantum machine learning. My professor is Professor Amlan Chakraborty, as Shamapada knows. I have worked with him for the last 11 years. He is director of School of IT, University of Calcutta, and also a senior scholar in Princeton University. He is also working in quantum domain for the last 15 years. So, cut the long story short, let me present the recent development in quantum cryptography, actually, because it's a vast area. Still, it is niche, but it's a vast area. I have picked quantum cryptography because the maximum traction will be on quantum cryptography for the next 2 to 3 years. Then quantum machine learning and quantum AI will come with its actual development phase. Sorry for my voice because I'm feeling bad because of my health issues.